Hey kids, we got bonding notes number 6 here, page 6. We're going to draw the Lewis dot diagram for magnesium nitride. Magnesium makes a +2 and nitrogen makes a -3 ion. In order to make this work, we have to crisscross this to Mg3N2. So to draw the picture, we're going to need magnesium with a empty orbital with a +2, and then we're going to need another one with a magnesium cation with a +2, and then we're going to need another magnesium cation with a +2. That adds up to +6. Now we're going to need 2 nitrogens. The nitrogen starts out with 5 valence electrons, and it's going to gain 3 electrons and become a -3. Then we need another nitrogen that has 5 valence electrons, and we're going to add 3 more electrons and make that -3. And what's important is +2, +2, +2, -3, -3 equals 0. We end up with a net neutral ionic compound in a 3-to-2 ratio. 3 magnesiums to 2 nitrogens. All right, we're switching gears now to talk about metals. Properties of metals that are important. Metals conduct electricity. That's key. That's a really good metal property. Metals are malleable. That means when you pound on them, they flex and they get thinner. They also are ductile. Ductile means you can turn them into a wire. Now, there's a whole lot of other metal properties, and we'll run through them right now. They have a relatively high melting point and a relatively high boiling point as compared to nonmetals or even a lot of other compounds. They have a low C value, a low specific heat capacity constant. They heat up really quick and they cool down pretty quick as well. They're actually fairly dense. Compared to nonmetals, they're pretty dense. There's a lot of properties. Metals have a lot of properties, of course. They conduct heat. I forgot that one too. They conduct heat. Anyway, the way metals are bonded together helps explain at least the top 3 main properties of metals: the electricity, the malleability, and the ductility. Metals are understood to be packed cations in a sea of valence electrons. Now, this is almost poetry. Packed cations in a sea of valence electrons. Now, this represents a small, thin piece of wire. It's a short piece of metal. You see all these plus signs? Those would all be individual atoms of metal. Make believe this is copper wire. In a piece of wire this long, there'd be millions, billions of atoms. This is a diagram. I can't draw pictures like that. Now, what happens is the atoms are not just stuck together. We imagine metals in a chemical way. How are they bonded together? They are packed cations. They call them the ion cores. Those are the packed cations. And then the valence electrons all come off and they all run around. They all run around. So if we were to hit this really hard with a hammer, say, that way, and we squish these cations together, when all the positive charges come close together, they would pull apart. I just bang the camera here. They'd pull apart and they'd crack. That doesn't happen because electrons will move in where there's closer positive cations. There'll be more electrons coming in to keep it neutral. When you pull a piece of metal, pull it, and it changes shape and distorts into the shape of a wire. As the cations get closer together, when you're pulling it, the electrons move in there. And also, if we were to run a wire in here and push electrons in, as more electrons show up over here, and we run a wire out, the electrons are going to leave this way because this piece of metal can only hold a certain amount of electrons. And if there's a push here, electricity is the push of electrons, they'll push out on the other side, kind of like a pipe full of water. If you push more water in on one side, water's coming out the other side. In this case, electrons in, electrons out. So by understanding that metals, the way metals are physically held together is packed cations, and they are awash in a sea of valence electrons. By squishing them, stretching them, or even running electricity through them, it allows for the properties of metals to exist. Metals are made up of packed cations in a sea of valence electrons. Smashing a piece of metal with a hammer will squish it flat. This is called being malleable. The flow of electrons is easy in metals, metals. Electrons just flow right through. And in a piece of metal itself, the electrons flow from here to there. This is almost like Dr. Seuss now. If you smashed it, made the cations tighter, electrons could move in to offset that excessively positive charge. In metals, I don't even know what we're going to say for this, but in metals, the electrons are loose and mobile. And because they are loose and mobile, it allows for the main properties of metals, their conduction of electricity, their malleability, and their ductility. These loose and mobile electrons allow this to happen. If the electrons were not loose, say in a piece of glass or in a big crystal of a salt, where the ionic compounds that form, they're bonded so tightly, or in the silicon dioxide, it's actually a non-metal, but the electrons are not loose and mobile. They're in the atoms. They're being shared between the oxygens and silicon. Those electrons are not loose and mobile. When you hit that solid silicon dioxide or hit that solid glass, you squish the positives together, and it cracks and causes the property of being brittle, and it cracks rather than distorts.